Okay, so today we're looking at Chem activity number 18, physical changes and energy. So the key takeaway to this first model is this equation, delta E equals E final minus E initial. And if you're taking physics, I guess it's a common, you might have encountered this equation already. So it was also later on described in Model 2, these energy diagrams, right? So we began this um, class period by dipping your finger in some water and, right, dipping it and just waving it around and try to feel the energy exchange, right? So you felt that your finger got cold, and then as you continued to just wave it around, wave it around, wave it around, it eventually became such a dry, but it eventually became um dry. It evaporated, right? That's what we said. Critical question, thinking question number one: what happened to the moisture? It evaporated. So what is actually happening in there is, assuming that our system is only the finger and the water on your finger, heat is actually getting out of your finger, right? So that almost dry, not not quite dry, but the heat in your finger is actually being transferred to the water in your hand or in your finger. That's why it evaporates, right? Energy in the form of heat is being transferred from your finger to the water. And when it gets enough heat, it evaporates, right? And take note as well. And if you've taken physics or are taking physics right now, whatever energy that one loses, the other gains, right? So the energy, the total energy is not lost. Like you're not making energy, like you're not gaining energy from nowhere, right? The heat is coming from your finger, and that energy, the amount of energy that your finger gives off, is the amount of energy, equal energy as well, that your um that the water receives, right? Okay, so an endothermic process is when delta E is positive. And when is that case? When your E final is bigger than your E initial, right? You have a bigger number and you're subtracting a smaller number from a bigger number, you'll get a positive number, right? Say, for example, this is 10. It is a bigger delta E, or a bigger E final, and your E initial is just 1, right? So 10 minus 1, that's positive 9. But if it were the other way around, that would be an exothermic reaction where delta E is negative, where delta E is less than 0. You have a smaller E final, say for example 1 minus 10. You have a bigger E initial. 1 minus 10 is a negative 9. So when we look at these are what we call energy diagrams, by the way. They show us um, how we know through a graph if the delta E, or the change in the energy, is positive or negative. So it asks us, right? It's like this. Now I want us to fill this blanks in. I know that this one is already written out in your Poggle, but I just want to um, write it out again right here. So the beginning end of an arrow, right? That part starts where your initial system is, and it points to the final state of your system. Now, if that doesn't make sense, what did we start as, right? We started as this liquid water on your finger. Now, We said that that liquid water evaporating, we said that that's an endothermic reaction, right? So that liquid water was our starting state. So where would I be putting liquid water? Again, in an arrow, this beginning mark right here is where what your initial state is, and it points to your final state. So your initial state in this case is liquid water. And what is your final state? When it evaporates, what happened to the water? It evaporates, it becomes vapor, it becomes gas, right? So it becomes H2O, gas. Does that make sense? Well, it might not make sense just yet, but when we move to the next one, right here, the exothermic reaction, the exothermic piece right here is the one that gave off energy. This system, water, receives the energy, endothermic, positive, right? Gains the energy. Now, what is a system that lost energy? It would be your finger, right? So your finger initially began as wet, and as you shook it off, shook it off, shook it off, it became dry, right? So beginning of an arrow is your initial state, and it points to your final state. The initial state of your finger was wet. And the final state of your finger, it became dry. And the overall energy, change in energy, delta E, in this system is negative, right? It's less than 0, it would be negative. Now, we didn't quite get to the experiment that we were supposed to do, but we were supposed to observe 3 different solvents. It was water, ethanol. Is it ethanol or methanol? Methanol. So it's water, methanol, and hexane. So what you were supposed to do was there are chem wipes set out like 1, 2, 3, and drop 10, do 10 drops of water on one, 10 drops of methanol on the other, and 10 drops of hexane in the other. And you're going to observe them evaporating. So that's the process that you're going to be observing. Now, when it asks you what is happening in this observations, it's evaporating. Quite similar to this one right here, where we had liquid water, it evaporated, it became vapor, water vapor, right? Or gas, H2O gas. Now, what does that tell us about these reactions that we have? Well, it must be that they are endothermic reactions, right? Next, one of the things that you'll be doing after you make these observations is that you're going to make an energy diagram for 3 of those solvents that you observed. Now, you see that, let me go back to this one for a second right here. Remember when I said whatever one loses, the other gains, right? And they're equal. That's why I try to do the best that I can so that they look equal. Let's see how the energy gained by this, it's about this tall, is the same amount of energy that this system lost, right? So they have equal magnitudes of energies, but different signs. Now, in the observation that you'll be doing tomorrow will look like this. Now, what do we notice? They have different delta E's, right? Different sizes of delta E's. This required the more energy because it's taller. This required lesser energy, and this system required the least energy. So whatever solvent evaporates the fastest needed the least energy to evaporate. And the system that took forever to evaporate meant that it's been taking energy from the atmosphere, from the air in the classroom, more energy, right? So the air in the classroom is, say, warmer than the system that you're dealing with. So the energy from the classroom gets into that solvent, right? Applies heat energy in the form of heat until it evaporates. So again, a system that needed more time to evaporate, right? Because more time means that more energy is being put into it, is the tallest. And the one that evaporated quickly would be the one that needed the least amount of energy to evaporate. And again, they all started from a liquid and they become vapor. They evaporated, right? So you're labeling this as whatever solvent, liquid, whatever solvent that is gas. You're starting from liquid, ending with gas, right? It's pointing to the final state of your system, which is gas. Okay, now let's look at different examples where this can be applied. Let me just pull this one closer. Okay, so I want us to differentiate between what an exothermic and an endothermic reaction is. Again, an endothermic reaction is a positive delta E, and a negative delta E is exothermic, right? Okay, let's look at this one. The first one, we have solid water or ice melting to liquid water at 0 degrees C. And it has a delta E greater than 0. So when you say that a number is greater than 0, that means it's positive. What did we say about positive delta E's? That must be endothermic, right? Because what's happening to the ice? If you set an ice just out in the open, it takes in energy from the air around it, right? Because the air is warmer than the ice. So air in the room just applies an energy until the ice melts. If it gains enough heat, it becomes water. What about this one? We have 2H2 gas plus O2 gas becomes H2O liquid plus energy. When your product is an energy, what does that mean? You give off energy, right? So this is your starting states, and they give off energy when you combine them together. What does that mean? Is that a positive or negative? Is that an endo or exo? When you're giving off energy, that means exo, right? Energy exits you. That's an exothermic reaction. So this is exothermic. What about in this case? We have 2HGO, mercury oxide becomes liquid mercury and oxygen gas. So if you need energy to do something, right? You need energy for something to happen. Energy has to be put into you. That means that's endothermic. Energy is coming in endothermic reactions, right? This is endothermic. What about the reverse reaction? If it's the reverse reaction, it's just the same thing, but I reversed it, this to an E. Now I've reversed it. Energy becomes a product, right? We're starting with this. You end up releasing energy. And when energy exits or gets out from the system, exits is exothermic. And lastly, we have methane gas reacting with oxygen in a combustion reaction. It, it is burning. It produces CO2, carbon dioxide, and liquid water. And we are given a value. Now it's a value that we have for delta E. We have negative 885.3 kilojoules per mole. We have a negative delta E. Now what does a negative delta E stand for? That means negative delta E is an exothermic reaction. Okay, make sure you go over the reading that's assigned for this class, and other problems that you might work on are in chapter 5. Yes, this is the introduction to chapter 5. So some of the quiz problems may come from those those readings. So make sure to be prepared for that. And yeah, phase changes and energy diagrams.